Okay, I think सभी लोग जुड़ चुके होंगे. So I think all are in now. Am I audible to all?
Yes. Yes, Mr. Pandey, you are audible.
Okay, sir. Thank you. My screen is visible now?
Yes, completely visible.
Okay.
Is visible to the audience.
Sir, screen is not visible right now, sir.
Yeah, trying for it.
Now visible, sir.
It is
Okay.
visible, sir. Visible.
Okay,
Yes, sir.
thank you. Is it visible?
Yes, sir. Completely visible.
Okay, thanks for this confirmation. So today I will be talking about nanofiber technology fabricated through a special process. We call it as electrospinning, and we try to explore these electrospun nanofibers as carriers for drug delivery. Now, if you look at the inspiration of this nanofiber technology, it is year-old. Like, so for example, the spiders, they try to make webs, and these webs of the web of the fibers made by these spiders are nothing but nanofibers. If you look at the nature, silkworm also produces silk fibers for the formation of their cocoons, and these silk fibers are also a very good example of nanofibers. So nature has created nanofibers million years back. But talking about electrospinning as a process of artificial manufacturing of nanofiber is an emerging technology. So it is basically a straightforward method for producing ultra-fine nanoscaled fibers. We call them as nanofibers. So basically why we call it as so electrospinning is a combination of two words, electro and spinning. So spinning is a technology whereby we produce fibers, and electro, basically we are using electrical energy for the preparation of these fibers. That's why we call it as an electrospinning process for fabrication of fibers. So basically we will be using strong electrical field on the polymer solution or polymer melt so that we can be able to produce fibers. So that's why we call it an electrospinning method. If you look at the historical development of this nanofiber technology, artificial manufacturing of these nanofibers, it started in the year of 1600, and so in the screen, the historical development is shown. And one of the key achievement was in the year of 1964, when Professor Taylor reported formation of a Taylor cone. So please keep in mind, in the subsequent slides, we will be talking more about this Taylor cone. So in the 1964, the Professor Taylor reported formation of Taylor cone. That was a significant milestone in the development of nanofibers. And If you look at the recent past in the 20th century, we have seen production of nanofibers using multiple spinnerets or needleless electrospinning. So these are the most advanced way of fabrication of nanofibers. Now, if you look at the concept, the basic concept is that this particular electrospinning process is an electrohydrodynamic process in which basically a liquid droplet is electrified in the presence of DC current supply to generate a Z, followed by stretching and elongation to generate a fiber. So basically, the concept is a liquid droplet is charged, and this by application of DC voltage. So this charged droplet will form a Z. Then that Z will get elongated, followed by stretching, and that forms a fiber. So that is the whole concept of electrospinning process. In subsequent slides, we will discuss in more detail about the process. Now, if you look at the various steps in the process of electrospinning, first of all, we need to form a Taylor cone. I was telling you in the 1964, Professor Taylor reported the Taylor cone. So basically, say for example, you are having a pipette, and from the pipette, when a droplet falls, you look at the formation of droplet at the orifice of the pipette. When the droplet falls, it is slightly elongated depending upon the viscosity of the fluid. If the viscosity is more, you will find that a thin stream of fluid will come out in the form of the droplet will be converted into a stream while falling due to the gravitational force. But if it is pure liquid, we will find that from the orifice it will form a sphere, and that sphere drops from the pipette. Same thing is happening in case of electrospinning. So the primary step in the process of electrospinning is that you need to form a Taylor cone upon charging a liquid droplet. So in this process, in the subsequent slides, we will be detailing in more detail how basically this Taylor cone is formed. So here you should keep in mind that we need to form a Taylor cone. Then, so that is basically a charged droplet, and that charged droplet stretches, and that stretched charged droplet subsequently thins and then solidifies, and after solidification of the Z, it will deposit it as a fiber. So this is, in these 5 steps, this electrospinning process is completed. So this is basically the electrospinning unit which I was having at my laboratory, and it was manufactured by IIT Kanpur. That is an incubation center at IIT Kanpur. Professor Dr. Sandeep Patil is there. He has basically manufactured this. Even at, if you are having a good mechanical engineering department, you can be able to manufacture the same equipment at your laboratory. So these are the various components of electrospinning. Basically, you need one syringe pump, you need a DC supply, you need some spinnerets, then you need some collectors. So these are the basically some components, basic components of the electrospinning unit. So now here we will be able to understand how the process basically proceeds. So basically, electrospinning is a process whereby you will see the fluid which is converted to form fibers, nanofibers. And then the blue colored is the symbolic representation of the working fluid. So this is the fluid. Basically, it is a polymer containing fluid, and you see this is the DC voltage supply, and this one of the electrode is attached to a metallic needle. So this is the syringe, plastic syringe, and then this is a metallic needle. And this DC voltage is electrode of the DC power supply is attached to this metallic needle. Now, when you will switch on the DC power supply, what will happen? This voltage will be applied here, and the other portion of this electrode is attached to a collector plate. This is a metallic collector plate. Now, collectors are various types that I will show you in more detail. So this is also metallic collector plate, and this is a metallic needle, and voltage is applied between the needle and the collector plate. Now, when you will push this syringe containing this polymeric fluid containing your work, basically we will call it as a working fluid, because it contains the polymer, it contains the drug, it is a blend of it, and some other excipients when it is needed. So when the syringe pushes the liquid, it will form a droplet at the orifice of the needle. Now, if there would have been no electric supply, then what will happen? You will find a spherical droplet forming at the orifice of the needle, and it will fall eventually due to the gravitational force. The gravitational force of the earth will make the droplet to fall from the orifice of the syringe to the bottom if there would have been no electrical supply. But here what happened, we have attached a DC voltage supply which supplies voltage. Now here I must tell you that the voltage applied here is in the form of kilovolts. Like usually we operate the equipment at 10 kilovolt up to 50 kilovolts. So my dear friends, you need to understand such a high voltage is applied. 10 kilovolt, our household voltage is 240 volts. But here we are applying 10 kilovolts to up to 50 kilovolts. So when, say for example, you have pushed the syringe, the droplet is formed at the orifice of the needle, and then before the droplet falls because of the gravitational force, we have applied the voltage, electricity. Now, what will happen? This is a metallic needle, and the droplet is formed at the orifice of the metallic needle. So the droplet is physically in touch with the needle, and the needle is basically now charged because it is metallic, it is charged. And the working fluid here is also conductive in nature. So the working fluid is conductive in nature means what will happen? The droplet formed, that will also be charged because of the conductivity of the metallic needle, which eventually passes the electrical energy to the droplet. Now, the droplet formed at the orifice of the needle is charged one. So what is the charge? It is somewhere around 10 to 15 kilovolts. And so this is, say, for example, cathode. And this is, for example, anode. Anode is the collector plate. So what will happen? This charged droplet, the charge in this droplet has to migrate from one electrode to another electrode. So what will happen? So the droplet will be now, so which was initially it was a sphere because of the gravitational force and the surface tension. So it was a sphere. Now because of application of the electrical force, it will be slightly pushed. So now imagine when a droplet which was sphere is now pulled from the bottom, it will form a cone. So that cone is called as Taylor cone. So in 1962, Professor Taylor coined the name Taylor cone for this formation, for this transition of a sphere to a cone under the influence of electrical energy. DC voltage, DC electrical energy. Now, so now what will happen? This Taylor cone will be formed. Now this Taylor cone eventually, when further electricity will be applied, that cone will be converted into a jet, and that jet will get elongated, and then it will be collected at the collector plate, because eventually a negative charge will come to the positive charge here. So the charge has to travel from one electrode to the another electrode. So the one electrode is the needle or the charge droplet, and another electrode is the collector plate. So the plate at the collector, the fiber will be formed. Now here there are some key formulation concept which affects basically the process of electrospinning. So basically the polymer solution, whatever you have kept in this syringe, that basically forms the fiber. So say for example, this contains a particular polymer like polyvinyl pyrrolidone K30. Then, and your drug is, say for example, efavirenz. Now the drug is dissolved in this polymer solution, and the solvent system you have to choose very judiciously so that you have to ensure that the particular working fluid is conductive in nature. So because conductivity is a key concept here, it should be conductive in nature. Now, what are the solution variables? You see the solution variables like concentration, how much polymer you are using, how much active ingredient you are using, how much other excipients, if any, you are using. So that is a key formulation variable. Another formulation variable is your conductivity. So another concept is conductivity. So conductivity of the working fluid is also critically important. So more the conductivity, more chances of formation of fiber will be there. And then another key important solution variable is the viscosity of the fluid. If it is too viscous, then again there will be problem in the formation of nanofibers. The morphology of the nanofibers will be badly affected. Then the molecular weight. Okay, molecular weight also influences the viscosity of the working fluid. Then that's why molecular weight of the ingredients you are using, most importantly, the molecular weight of the polymer you are using is critically important. And then the solvent volatility is also crucial. Why? Because to get a dry nanofiber on the collector plate, the solvent has to evaporate during the flight of the materials from this needle, that is we call as a nozzle, from this nozzle to the collector plate. During the flight of the materials from, or the fiber from the nozzle to the collector plate, the solvent has to get evaporated, and only dry fiber has to be collected on this collector plate. So this is why the solvent volatility is also critically important. Now, if you look at the environmental variables, that is also influencing the process of electrospinning. Now, humidity is directly related to the volatility. So, subsequent, eventually you need the fibers to be dry. They are not sticking to each other. So, to get dry fibers on the collector plate, humidity has to be low. If it is highly, the humidity is high, then the drying of the fibers will be, the rate of drying of the fibers will be too low, and you will get fibers sticking to each other. So naturally, temperature is also important. You need to have temperature maintained throughout the process of electrospinning, not too high, not too low, exactly the right temperature for drying of your fibers. Then the Equipment variables are also there. The process variables are also there in the process of electrospinning. Like, say, for example, the distance from the tip of the needle to the collector plate. This distance is also very important because if the distance is too low, you are not able to get thin fibers. And if the distance is too high, probably you will not be getting eventually any fiber on the plate. So right distance between the nozzle and the collector plate is important. Then voltage, how much voltage you are applying, higher the voltage, higher the chances of formation of fine fibers. But there is again a limit depending upon the viscosity of the working solution. You have to optimize the voltage of operational voltage. And in the flow rate, in the first few slides, I was telling you the basic components of the electrospinning process. And there I told about a syringe pump. This syringe has to be pushed using a syringe pump.
Sorry, sir.
Yes.
I think the slides are not moving.
It is the same slide.
Oh, sorry, sir. Sorry.
Yeah.
I think you are talking about the few slides now. That's why.
Yeah, it is the same slide. So now what is the slide? It is reading electrospinning basics, is it? Excuse me, anybody confirm what is the slide reads? Is it electrospinning basics?
Sir, it is the first slide. First slide
only.
Yes, sir. That's why.
Last 30 minutes, only first slide is visual, sir.
Is it now visible? Is it changing the slides?
Yes, sir. Now they are changing.
So I came to this slide, basically I was trying to explain electrospinning basics. So no issue. I will briefly cover again. So what I was telling you is basically this is the electrospinning equipment which I used to have in my laboratory, and these are the various components of electrospinning. Is it visible, the components of the electrospinning? A syringe pump, a DC supply, a spinner, it is there, and then there are collectors. Fine. So in this process, basically, there are various variables like what the solution you are spinning, what is the nature of the solution, what is the concentration, conductivity, viscosity. So these are the solution variables. And then there are environmental variables like humidity, temperature. So they also influence the quality of the fibers production. And then there are electrospinning variables, which is basically process variable. What is the distance between the needle tip and the collector plate? That is also influencing the process of electrospinning. And then the voltage of the operational voltage, how much voltage you are applying between these two electrodes, that is also going to make sense. And then flow rate. I'm using a syringe pump here to push this automatically. The flow rate typically is sometimes 1 ml per hour to sometimes 5 ml per hour. So this is the range of flow rate we often use in the process of electrospinning. Sometimes in the micro level also you need to go down depending upon your formulation considerations. And then what type of collector you are using, that is also important. So this is the collector where the fibers are collected. Now you see, if you want to collect a mat of fibers, now if you refer to literature, you will find that this nanofiber mats are used for wound healing process. Now in that case, probably as a transdermal patch kind of thing you are preparing, then it is we call it as a nanofiber mat. So in that mat, the fibers are not woven. So they are non-woven fibers. Now, in a layman's language, if I will try to explain what is an woven fiber and non-woven fiber. Now, when we are flying kites, you see that the fibers are basically wound over a drum. So it is a continuous string wound over a drum. So it is a it is an woven fiber. Now, when it is a non-woven, now say for example, you have a big string, and that string you compress in your palms to form a disc. So that is a non-woven fiber. Now you just imagine when these fibers are falling on this collector plate, what would be the nature? They will form randomly. They will be collected over this plate. Now, instead, if you will having, say for example, this kind of a collector. Now you see a drum kind of collector. Now what will happen when the fiber will come? It will be attached over here, and this drum is basically it is attached to a motor, and this drum will rotate. Then what will happen? The fibers will continuously be wound over this drum. So you will get continuous woven fibers. So based on your requirement, static plate like this. So this is a static plate. So based on the requirement, you can switch between a static plate to a dynamically rotating drum. So these are the various factors that are involved in the process of electrospinning, and the point of action are also being listed over here. So basically the property of the electrospinning fluid, like viscosity, electrical conductivity, and surface tension, they affect the fiber morphology and the fiber diameter as well. And then operational conditions like voltage, the needle size, the spinner rate to collector distance, and the spinning solution flow rate. So these are also the operational conditions which influences the nature of the fiber that is formed. And then ambient conditions like temperature and humidity, they also influence the fiber formation. So this is again another systematic schematic way of representation of this electrospinning process, where basically the polymer solution was kept inside the syringe is pushed, the droplet is formed at the orifice of the needle, and because of this high voltage power supply, the droplet is elongated, and that Taylor cone is formed. The Taylor cone forms a jet, and jet eventually dries off because of evaporation of the volatile solvent, and then these dried fibers, elongated fibers, will be collected over this collector plate. So this is basically the gradual formation of drop to a liquid jet. So this is called as the Taylor cone, and this Taylor cone forms a jet, and that jet elongates. That jet elongates and then dries, and then eventually this liquid jet, when the volatile component evaporates, the liquid jet will be converted to a stretched, dried fiber, and that fiber eventually will be collected on the collector plate. So this is the actual image of the what is basically happening during the process of electrospinning. So you can see here, this is the metal needle spinneret, and at the orifice of the spinneret, you can see this is the droplet formed, and the droplet from the orifice of the droplet. So this is basically a Taylor cone. This droplet, a Taylor cone will be formed, and at the tip of the cone you will find the formation of the jet. So this jet will be formed because of the high voltage electrical supply, because it is charged. So this charge will try to move towards the oppositely charged collector plate. So during its travel from this this electrode, needle electrode to the plate electrode, it will be elongated, and the solvent volatilizes, and you will get dried fibers collected on the collector plate. This is how eventually you will find fibers, and these fibers will deposited on the other side of the collector. Now, so this is a simple needle-based electrospinning process, and now we are having some advancements, like we have multiple needles. You can have coaxial, triaxial spin rates, needleless free surface electrospinning is also gaining a lot of momentum nowadays. And then I was talking about working fluid. Why I was talking about working fluid? Because sometimes solvent-less electrospinning also possible. So in that case, we are using melt electrospinning process, when the polymer and the drug, instead of they are solubilized in a suitable solvent, the polymer is molten, and to the molten polymer, a drug will be added. So the drug will be basically dispersed in the molten polymer, and then that melt is spun using DC voltage. So that's what we call the melt electrospinning process. And then finally, the recent year, we are having AC electrospinning as well, but it is dangerous to use. So mostly in the laboratory setups, we are using DC electrospinning, but there are a few papers you will find in the scholarly literature talking about AC electrospinning as well. So one of the fundamental problem with the single needle electrospinning was its output. Now, when you are using a single needle, and the flow rate I told you about 1 ml per hour or 5 ml per hour, if you will run this electrospinning device for the whole day, hardly you will be able to spin some 100 ml or 200 ml or 500 ml of fluid. But beyond that, it is not practically feasible to spin more amount of working fluid. So to handle that, we are now having multi-needle electrospinning process. So this is the spinneret. You see there are multiple needles are attached to the spinneret. So to the other side, the syringe will be attached, and subsequently the syringe pump will be there. So that will push the fluid. So the fluid will be coming out from all those needles. So thereby the output will increase. So this is also another design of the multiple needle electrospinning. So this is a plate shape design. There is a parallel spinning process. So all these are
Dear audience, actually there is a network issue on Dr. Patnaik sir screen. Kindly wait for a while. Our technical support team will contact to Dr. Patnaik sir, Mr. Ritik Verma sir, Assistant Professor, and Mr. Soumati Mukherjee sir, Mr. Akash Garg sir. Kindly contact to Professor Patnaik sir. I think Dr. Patnaik is facing some problem. So we will wait for some time. Yes, Bhavnagar, you raised hand. You ask any question? Bhavnagar, kindly ask your question.
I'm extremely sorry. Actually, I didn't know when I was got disconnected.
It's okay, sir. It's okay.
Okay, sir, no problem.
It's okay.
Bhavnagar, you can ask your question.
Yes, any questions so far?
Okay, I think, sir, you can start your presentation.
Huh. So here, basically, we are having a concept like coaxial electrospinning and triaxial electrospinning. Here, basically, instead of a single needle, we are using multiple needles, and thereby the output of the electrospinning process will also improve. Now, in a layman's language, when I try to tell about the process of electrospinning or electrospun nanofibers, I always give the example of a microsphere. Now, in the say for example, a microcapsule, say for example, what is a microcapsule or a microsphere? The active ingredient is dispersed as a core in a polymeric system. Now, in a microcapsule, what happens? Core is the drug and the coat is the polymer. And in a sphere, you will find that core, there is no significant core, but the active ingredient is homogeneously dispersed in the polymeric system. Then that is a microsphere. Now take the case of a microcapsule where there is a distinct core and there is a coat. Now you just pull that microcapsule from the two ends. So what will happen? Microcapsule was initially a sphere. When you will be pulling it from the two ends, it will form a cylinder. So a sphere is converting into a cylinder. Now you further elongate, you will find it will form a fiber. So the same thing is happening in the case of electrospinning. Now here what happens? Now if you are having a coaxial electrospinning process, the needle is coaxial, meaning that there will be, say, is my slide visible? So here basically you will find there is one needle and inside that there is another needle. So this is a concentric needle. So needle inside a needle. So the inner needle, say for example, carries the drug fluid and the outer needle carries the polymer solution. Then it will form a droplet at the orifice of the needle, which is basically the core is made up of drug and the coat is made up of the polymer solution. Now the droplet when it will form a fiber, you will find that this is a fiber where the core is made up of drug and the sheath or the coating is of polymer or any excipient, whatever you are using for the fabrication. So eventually, if you are having 3 needles like this, you will get, say, for example, 3 different kind of drugs you can incorporate into a fiber, and that sheath will be the polymer sheath. So, for example, you have incompatibility issue with your drugs, and you are trying to formulate a fixed dose combination of some active ingredient. These 3 drugs can be incorporated into a single fiber morphology. So this is another advancement in the process of electrospinning. We call it a triaxial electrospinning process. Now, this is the ACM of electrospun nanofibers. You see here, you find a distinct core and a distinct coat material. And this in the triaxial electrospinning, you find 3 chambers, and this is the core material. So this is basically another method of electrospinning where we are having multiple channels to deliver the working fluid. So needleless electrospinning is an advancement in the electrospinning process where the nanofibers, they start forming from the surface of the molten working fluid or solubilized solvent-based working fluid, but not much work has been done in this needleless electrospinning. And similarly, melt electrospinning also, we find a limited literature on melt electrospinning, where instead of polymer solution or any solvent system, we are using the melt only. So naturally, melt electrospinning will be a more greener approach compared to the solution electrospinning process. So nowadays, we are talking more about green pharmaceuticals. So melt electrospinning will be an option for us to work on green pharmaceuticals. Similarly, the DC electrospinning is commonly used. AC electrospinning is rarely used. Limited literature support for AC electrospinning. And if you look at the various types of nanofibers, based on the spinning process, you can have a simple matrix type of nanofiber. Then you can have simple core sheath type of nanofiber. Then you can have a Janus structure, then inclusion complex type nanofiber. Now, in simple matrix type nanofiber, basically, the working fluid is basically you have to choose a solvent system, solubilize the polymer, then you dissolve the API, other excipients, you get a homogeneous dispersion of the polymer, drug, and the excipient in a suitable solvent system, make it conductive, apply the electrical charge, and then you get the fibers. So this is simple matrix. The drug is homogeneously dispersed in the fiber system. And you can have a core sheath type of nanofiber using coaxial or triaxial spinnerate. So basically, you will have multiple solution feed system. One solution feed will be, say, for example, so this is a core sheath nanofiber spinnerate. Here, the inlet for the core fluid is different, and the inlet for sheath fluid is different. So, say, for example, if a range nanofiber you are preparing, then if a range dissolved in a suitable solvent will be pushed into this syringe, and then through another passage we have to push the polymer solution. For example, polyvinyl pyrrolidone in ethanol. That solution you can push into it, and resultant you will get the droplet will be formed. The droplet pore will be, so it is a liquid droplet, and the pore is the drug, if arranged, and the sheath will be, say, for example, the polymer system, whatever you have taken. So this is the SEM image of a core sheath nanofiber where there is a distinct core of 490 nanometer and there is another sheath of around it is 220 nanometer. So there will be various, merits and demerits of using. I mean, say what type of nanofiber system you want to have. That will be based on the desired application of the nanofiber. Say, for example, whether you need a matrix tablet or you need a coated tablet. So same thing is here. Do you need a matrix fiber or you need a core sheath nanofiber? Now, another interesting thing is Janus nanofiber. Now, Janus is a Greek god. It's a god of gates. So this particular god has had two faces. One face is the two faces are of different appearance. So I mean to say, so whenever in nanotechnology you are preparing a composite nano structure where you are having two different properties, then we call it as a Janus nanocomposite. So here nanofibers can also be of Janus nature, where you can have two different phases. So for example, side by side spinneret, then you will eventually will get a Janus structure. Now, in core sheath nanofiber, now if you can look at this image where the cursor is moving, you will find the structure of the Janus spinnerets. Here you can see that the internal syringe, internal needle is not concentric. Basically, it is eccentric. Eccentric means it is attached to the periphery of another housing needle. So this way you will be able to get Janus structures. So if you are using concentric needles, you will get core sheath nanofibers. If you are using eccentric needles, then you are getting Janus nanofiber. So that is the take-home message over here. Now, the nanofibers have been used in drug delivery system basically for sustained drug release or modifying the drug release pattern. So far as my lab is concerned, I have been working on nanofibers for improving the solubility of poorly soluble drug candidates using the concept of homogenization, and then I'm talking about the concept of solid dispersion. So the nanofibers, you can have solid dispersion nanofibers. Amorphous solid dispersion nanofibers are also feasible. So these nanofibers has been used for prolonging the drug release. You can use a matrix type, core sheath type, other systems. And then apart from this, for multiple applications, you can use these nanofibers. So this is the electrospinning device, and this is my lab where I was working on electrospin nanofibers. And these are a few publications which appeared in Drug Development Industrial Pharmacy, White's Nanomedicine, Ectochemica Pharmaceutica. So these are the few of my PhD scholars. They are working on this nanofiber technology, and few are in the pipeline as well. So thank you very much. I understand there was difficulty in my connectivity. So if there is any issue, I beg your, you should pardon me. So any question, please? Any question from the audience?
If you have any question, raise your hand and ask. Now it's your chance to ask question from Dr. Patnaik, sir. Yes, please, Sarika Chaturvedi, you can ask your question. Kindly open your mic and ask the question. I think no one. Thank you so much, Dr. Satyanarayan Patnaik, sir, for your insightful
Thank you,
presentation
thank you.
on electrospun nano fiber platform for innovative drug delivery. Today, we explored the fascinating world of electrospun nano fiber platforms for innovative drug delivery, covering electrospinning basics, components, properties of electrospinning fluid, operating conditions, and ambient conditions. I am grateful to Dr. Satyanarayan Patnaik, sir, for sharing his expertise with us. And
Thank you,
that's
Dr. Pawan.
for day 3, our faculty development program. Thank you so much, sir. Today, we explored the fascinating world of electrospun nanofiber platforms for innovative drug delivery. And I'm grateful to Patnaik, sir, for sharing his expertise with us. And heartfelt thanks to Dr. Himanshu Chopra, sir, Director of Rajiv Academy for Pharmacy, Mathura, and Dr. Devendra Pathak, sir, President of Mathura Local Chapter, for their valuable support. This is the time to give special appreciation to our energetic organizing committee members, Assistant Professor Mr. Akash Garg, Mr. Ritik Verma, sir, Mr. Soumyadi Mukherjee, sir, and Vibha ma'am for their dedication and hard work in making the third day faculty development program success. I would like to thank you, Organizing Secretary Dr. Mayank Kulsresh, sir, and thank you, our respected associate professors and all assistant professors involving this faculty development program who are seeing this faculty development program. Thank you so much to all. Thank you, audience, for carefully listening. Thank you so much.
Thank you. Bye-bye.
Thank you, sir. Thank you so much.
Thank you, sir.
Bye. Thank you, sir. You can leave the session now.
Pawan sir, provide the PPT also of the session.
Yes, you will get that.
Okay, dear. Okay.